Hello everybody, and welcome to this session of Black Hat Europe 2020. In this talk, I will give you a slightly unconventional view of the relationship and implications between quantum computing and cryptography. It is a great pleasure for me to be here with you today, and because it's the first time that I present at Black Hat Europe, I will start with giving you a short introduction about myself. My name is Tommaso, I'm a mathematician. I got a PhD in cryptography and in particular on the topic of quantum security. I was a researcher at IBM Zurich from 2017, and starting from 2019 I joined Swiss-American cybersecurity company Kudelski Security. In this talk, I will start with a short introduction to quantum computing. I will go in detail looking at the relationship between quantum computing and cybersecurity, with a particular focus on cryptography. And then I'm going to talk about so-called post-quantum cryptography, and I will explain you why this is not going to be a panacea. And finally, I'm going to delve into the very complex topic of quantum cryptography. So I will start with quantum computing, and for those of you who have never heard before of quantum computing, this is a new computing technology being researched, actively researched right now, and these are machines that work on physical principles that are quite different from the classical principles of 0 and 1 that are at the basis of every classical computer nowadays. Quantum computers work according to the laws of quantum mechanics. This gives quantum computers an advantage in solving certain problems, which becomes very interesting for many applications, as we will see, but also introduces certain difficulties, certain challenges in building these computers, which are in fact very, very difficult to build from an engineering point of view. In fact, we don't really have anything more than prototypes right now. These prototypes work though, they're just not very powerful yet, but the situation is improving very fast. So in order to understand how a quantum computer works, the first thing we want to do is to look at the way a quantum computer represents information that can be used to perform useful computations. This is a little bit different from what happens in a classical computer. Let's recap what happens in a classical computer first. Classically, a computer works on bits, which are elementary units of information that can be 0 or can be 1. They represent, for example, the state of a coin that can be heads or tails. But how do you represent the state of a coin that is spinning midair? Well, there is another representation for this kind of process. It is called a probabilistic bit. A probabilistic bit is an elementary unit of information in the presence of uncertainty. It can be 0, it can be 1, but it can also be something in between 0 and 1. So 0 with a certain probability and 1 with another probability. Which means that a probabilistic bit can represent a state which is, if you want to see it geometrically, it's any point on a segment between 0 and 1. You can also say that a probabilistic bit can be in a state that is a superposition of heads and tails. So when your spinning coin eventually lands on a surface, for example on a table, an observer is going to look at it, and the outcome of this observation is going to be either head or tail. So it's going to still be 0 or 1. The difference is that now this is going to be a probabilistic process. After the observation, you don't have a spinning coin anymore, so your coin has collapsed on a classical state, but the outcome of this observation is probabilistic. A quantum bit, or also called qubit, is the elementary unit of quantum information. And it's exactly like a probabilistic bit. The difference is that now these probabilities are actually complex numbers. So they are mathematical structures that are a little bit more complicated. And if you try to represent it geometrically, it turns out that you cannot use a segment between 0 and 1 anymore, but you have to represent a sphere. So a qubit is an arbitrary point on the surface of a sphere. It can be 0, can be 1, or it can be any complex superposition of 0 and 1. So your qubit represents a quantum spinning coin. By the laws of quantum mechanics, when an observer goes and measures the state of a qubit, the observer will not see a superposition. The observer will again see either 0 or 1. So only one bit of classical information from the measurement. But this is again going to be a probabilistic process, and the distribution of 0 and 1 depends on the complex numbers that describe the state. Qubits can also be manipulated, so you can perform operations that perform some state change on your qubits. And again, by the law of quantum mechanics, these operations that are called quantum operations or unitaries are represented by reversible mathematical matrices. Again, it's not important now to look at the detailed formalism of how these things work. The only thing you have to remember is that when you have qubits, you have two possible operations, two possible classes of operations, either reversible operations or measurement operations that destroy the qubits and output classical informations. Qubits exhibit properties that are very inherent to their quantum nature and cannot be explained in classical terms. For example, entanglement. Entanglement is a property of system of many qubits that cannot be described by looking at the single qubits in isolation. In other words, a system which is made of entangled qubits has to be seen as a big system where the state of the single qubits cannot be described independently from each other. An interesting consequence of this that has also been observed experimentally is the following experiment. So if you take an entangled system and you split it into halves and you separate them by huge distances, then what happens to one of the two halves of the system, for example, an observation, has an immediately and measurable effect on the other half, even at huge distances. A lot of things have been said about this paradox or this spooky action at distance. It has been said that it violates Einstein's relativity because this action is faster than light. It has been said that it can be used to teleport instantaneously matter from two remote locations. No, nothing of this is true. So instantaneous action is not instantaneous transmission of information. And entanglement does not violate any known laws of physics. On the other hand, something that is relevant for us and is a consequence of entanglement is the following result in theoretical physics that is called the no-cloning theorem, which says that there is no physical operation that creates a copy of a given qubit. What does it mean for us? It means that quantum information cannot be copied. You cannot make a copy of an arbitrary qubit. And this is going to be a lot of interesting applications for us, as we will see later. So now we have all the ingredients for a recipe or a blueprint for a quantum computer. So that's how a quantum computer works from a basic point of view. You start with a physical system that represents your quantum memory. This system has to be a physical system that shows quantum behavior. And then you are going to apply a sequence of operations to manipulate your qubits according to a quantum algorithm, to a logical procedure that describes what you want to do. So first you initialize your memory in a certain state, and then you apply operations to manipulate this memory. At the end, you are going to measure the state of your quantum memory and obtain a classical result. What I just sketched here is a quantum circuit. These boxes, these quantum operations, are also called quantum gates, and they are the quantum analog of the Boolean gates that we know from classical circuits, and or not, just that in this case they are going to be reversible unitaries, reversible matrices. This circuit is a model to represent quantum algorithms. That is the way quantum computers manipulate quantum informations to do interesting things. Before talking about the many interesting things that a quantum computer can do, let's talk about what quantum computers cannot do. First of all, remember, because there is a lot of hype around quantum computers, so it's important to separate facts from fiction. First of all, building qubits and manipulate them is very difficult because a lot of engineering difficulties arise from the fact that these qubits are very delicate and they can be disturbed very easily. In fact, the qubits that we have nowadays that are at the basis, are the quantum memory where modern prototypes of quantum computers work, only last for a few milliseconds. Furthermore, even from a theoretical point of view, quantum computers are superior to classical computers only in a very thin meaning, in the sense that, for example, you can always simulate a quantum computer with a classical computer, of course, with an overhead. And most importantly, we have proofs that quantum computers, in theory, can provide a minimal speed-up, minimal theoretical speed-up on computational problems, but this speed-up from a theoretical point of view, again, is very minimal, and we have only speculation for a few candidate problems that we know how to solve on quantum computers efficiently, but we don't know how to solve efficiently on classical computers. So you might wonder, why is this all interesting then? Why are we even talking about quantum computers? Well, there is two reasons. The first reason is that this modest theoretical speed-up translates to huge speed-up for many real-world problems. In particular, there is Grover's algorithm, that is a quantum algorithm, so a procedure that you can only run on a big quantum computer, that offers a quadratic time speedup. Quadratic time speedup is nothing from a theoretical perspective, but it translates to a speedup from centuries to hours for many real-world problems, such as chemistry, logistic optimizations. So there is a lot of civilian applications that can have can benefit a lot from quantum computers. But I'm not going to talk about this here. I'm going to talk more about the second reason why quantum computers are interesting, and the reason is that those few candidate problems that I mentioned before that are easy to solve on a quantum computer, but we don't know how to solve on a classical computer, are actually very important, because these are problems, such as integer factorization, that are at the base of the security of many modern crypto systems that we use nowadays to secure our digital infrastructure, and they are used everywhere in the digital world nowadays. I'm talking about schemes such as RSA, elliptic curves. All these schemes are broken by a quantum algorithm that is called Shor's algorithm. So on one side, you have to see quantum computers as a resource because of the many civilian applications. On the other side, you have to see them as a threat for cybersecurity, because when a large enough quantum computer is going to be built, then all these schemes that we consider secure nowadays are going to be broken. Luckily, there are countermeasures against this, and they are divided into two broad categories. One is quantum cryptography, and one is quantum resistant cryptography, or also called post-quantum cryptography. In the next part of the talk, I'm gonna look a bit more into detail into these two countermeasures. I want to say just that I lied a little bit because there is not really just two classes, there is more classes of countermeasures. There is pretty much a spectrum, and especially two classes like superposition-based cryptography, superposition-resistant, and hybrid cryptography are very interesting for applications, but I'm not going to talk about this here. I'm only going to talk about the two main classes that are quantum resistant and quantum cryptography. Let's start first with quantum cryptography. Quantum cryptography is a form of cryptography that exploits quantum effects to protect information. And I'm pretty sure that when I say quantum cryptography, many of you are thinking of Alice and Bob exchanging photons on quantum channels. This is called quantum key distribution, and it is actually a very narrow field of quantum cryptography. It is mistakenly very often called quantum cryptography, but it's actually a subfield. This application exists nowadays, it's commercially available, you can buy it, you can implement it. It works, but it has special requirements, and it has a very narrow scope. You can only use it for a very specific cryptographic task. I'm not going to talk about this here, because it's not going to be interesting for this talk. Plus, there is many talks about quantum key distributions around. What I'm going to talk about instead is general quantum cryptography. This is a form of cryptography that you run on a quantum computer to protect quantum data. And this is completely different game field. In particular, you can use it to protect not only classical but also quantum data. You cannot use it nowadays because, as I said, you need a good quantum computer to use this form of cryptography, but it is going to be useful one day when quantum networks are going to become available. I'm going to talk about this in a bit. Quantum-resistant cryptography instead is something different. This is very often called post-quantum cryptography, which is a terrible name. I don't like it. I will explain it. I will explain why in a bit. This is cryptography in the traditional sense. You can run it on your laptop, on your smartphone, but it's based on mathematical problems that are so hard to solve that they are believed to be resistant even against future powerful quantum computers. So this is cryptography that you can use today, but it's going to be resistant against quantum computers of tomorrow. However, it has some drawbacks. For example, it is not as efficient as old-style cryptography, so like RSA or whatever. It is very hard to evaluate the security because it's a relatively recent field. There is a lot of research ongoing, and this is why NIST started a standardization process in 2016 that is still ongoing, which aims to select the quantum-resistant standards of the future in the same fashion as AES or SHA-3 were selected. There's still a few years before the process is concluded, but already the candidates that passed to the third round are pretty good. It is unclear when quantum computers are going to be powerful enough to threaten RSA, but the thing I want you to understand is that you don't have to wait that quantum computers are available in order to use quantum-resistant cryptography. Actually, you should not wait. You should start as soon as possible, otherwise it's going to be too late. And this is the reason why I consider the term post-quantum very misleading. Let me explain you a little bit better. Because a question that a lot of people ask very often is, when is it time for me to start switching to quantum-resistant cryptography? I ask you to consider the following. Consider the time that you need to research and standardize quantum-resistant cryptography. We are still at this point. Once you have the standard, you will need time to deploy the new cryptographic schemes on the field. Just think of how there are still many applications that are not based on AES, but they are based on the insecure 3DES, for example. Once you start deploying cryptographically quantum secure tools on the field, you still have to deal with old quantum vulnerable devices, schemes, services that still have to retain their security for their lifespan. And if you do A plus B plus C, and the time span is longer than the time necessary before scalable quantum computers are built, then you are already in trouble. It's already too late. So in other words, you have to see quantum-resistant cryptography as a form of insurance for what you have today. So for the data you want to protect today against future threats. But if you wait too long before starting to use quantum-resistant cryptography, it's going to be already too late. In particular, this means that post-quantum is actually pre-quantum. You don't have to wait that quantum computers become available, you have to start before that. This is the reason why I don't like the term post-quantum, I stick to quantum-resistant. But what about future assets? So what happens after quantum computers are being built? Well, quantum-resistant cryptography will still be secure, possibly. However, it can only protect digital information. But what if you have quantum data at some point? You cannot use quantum-resistant cryptography to protect quantum data. So how are you going to do? And why should you worry about this scenario? Let me answer the second question first. And let me talk to you about quantum networks. You remember what happened with ARPANET. It was only a few years from a situation where a few nodes were connected to a situation where this connection exploded, and you see where we are nowadays. In the same way, we can imagine that when quantum computers start becoming available, naturally they are going to be interconnected. There is a lot of research going on this. This is called quantum networks. The main point is that what history teaches us is that when a new computing technology becomes available, the next natural step is to connect these computing nodes into networks. And quantum networks are going to be the natural evolution for quantum computers. Quantum networks are going to happen in steps. There's going to be first step point-to-point links, second step entanglement-based links, so links that can exchange entangled qubits, fully corrected so channels that can exchange quantum data directly from the qubit memory of a computer to the qubit memory of another computer, up to a stack of fully corrected network protocols. Think of it as a quantum internet. Each one of these stages will enable new cool applications that are just it's going to be not possible to secure using traditional cryptography or even quantum-resistant cryptography. And we are already at the second stage. So this thing is already evolving in a parallel way with quantum computers. And in order to exploit these applications, in order to make them secure, you cannot encrypt ones and zeros. So you have to keep in mind that quantum-resistant cryptography is going to have limitations. This is why I'm saying you are probably doing it wrong. And it depends on the following question. What kind of person are you? Are you the kind of person who thinks that quantum computers are never going to be built? Well, in this case, you don't have to worry about all this. You don't have to worry about NIST. You can keep using RSA if you want. However, I have to warn you that your point of view is a minority view among experts and also goes against the evidence, because in the last few years, believe me, we have witnessed huge, incredible exploits in the development of quantum computing technology. On the other hand, if you think that quantum computers are going to be built at some point, then you have to accept the fact that quantum-resistant cryptography is not the ultimate security solution that some people want you to believe it is, because it's going to be only part of the solution. Not because of the security, but because of the functionality. Because quantum-resistant cryptography, the NIST protocols, only protect digital data, not quantum data. And at some point, we are going to have to deal with quantum networks that are going to coexist with classical networks. And for classical networks, you can use quantum-resistant cryptography, but for quantum networks, you have to use something different. Okay, well, maybe, as I said, quantum networks are not going to replace completely classical networks, but they are going to be increasingly a part of the network infrastructure that the real world has to deal with. And at that point, in order to secure these networks, you need something else. And this is where quantum cryptography comes into play. So, in order to explain how quantum cryptography works, let me start with a simple example. The classical OneTime Pad. This is the simplest encryption scheme you can think of in the classical world. You have a message, you have a key, these are bit strings, and you generate your encryption by doing a bitwise XOR between the bits of the message and the key. One bit of message, one bit of key. So what I'm going to show you now is the quantum OneTime Pad, the quantum analog of the classical OneTime Pad. It works in a similar way, but the setting is a bit different here because we want to encrypt a quantum message. So a message made of qubits. Your key is still going to be classical, but the message is a quantum state. How do you do this? The first thing you do is you split your classical key into pairs of bits. Each pair of bits selects 1/4 elementary gates that are called Pauli operators. They are represented at X, Y, Z, I. These are the traditional way of calling them. These are the quantum equivalent of the NOT gates. So classically, you only have one NOT gate. Quantumly, you have 4 of them. This is a quantum property of information that you need 4 gates to mask one qubit. So you split your classical key into a pair of bits. Each bit selects one of these 4 operations. Each one of these 4 operations is applied to one different bit, qubit of your message. And at the end, you recollect the processed qubits and you have an encrypted quantum ciphertext. In order to undo the encryption, like in the classical OneTime Pad, you do the reverse process. The core observation here is that you need 2 bits of classical key for every quantum bit of the message. So this is a crucial difference between the quantum and the classical case. But now you might wonder, well, classically, the OneTime Pad is a very insecure scheme. Is the quantum OneTime Pad any better? Not really. The quantum OneTime Pad is as insecure as the classical OneTime Pad. It's just an example. Can we do something better? Yes. How do we encrypt in a secure way a quantum message? Again, the setting is you have a quantum message and a classical key. The way you do it is, first you generate a one-time fresh random key. You use this one-time key, classical key, to encrypt your message with the quantum OneTime Pad. But then you also encrypt your one-time key with your classical key using a classical encryption scheme. What you obtain is a hybrid quantum classical ciphertext. And in order to undo the encryption, first you use the classical encryption to decrypt the classical part. So you recover the one-time key, and with the one-time key, you undo the quantum OneTime Pad. This classical encryption, this works both for symmetric key encryption and for public key encryption. So you can use AES as a building block to encrypt your quantum messages, and also you need AES and the quantum OneTime Pad, or you can use a public key encryption scheme and the quantum OneTime Pad. But for public encryption, you shouldn't use RSA because RSA is not quantum secure, so you should rather stick to one of the quantum resistant NIST candidates. The next step after encryption is authentication. In the classical world, you would use something like AES GCM or HMAC. Let's stick to HMAC, that is simpler to explain. In this case, in the classical world, your goal is to authenticate a message. You start with your message. first you encrypt it and you obtain a ciphertext, and then you apply an HMAC and you obtain your authenticated ciphertext. And what you would do in order to authenticate it, first you receive the ciphertext, you check the HMAC. If the HMAC is valid, you decrypt the ciphertext. But here we have a problem. We don't have an analog of the HMAC system in the quantum world. Why? Because in practice, what you do with the HMAC is you apply a hash function. A hash function is a one-way procedure. But we have already discussed that in the quantum world, operations have to be reversible unless you want to destroy the quantumness of your state. But you want to be able to recover a quantum message. So, in other words, you don't have an analog, a quantum analog of a hash function, and so this system doesn't work. What you have to do instead is something slightly different. You start with a quantum message and your classical key. The first thing you do is you pad your quantum message with a quantum state that is only 0 qubits. At this point, you use your classical key to apply quantum permutation to your quantum key. This is a reversible operation that is a bit more complicated than a quantum one-time pad, and it allows you to obtain a quantum authenticated ciphertext. This scheme looks pretty simple. Intuitively, it works. The idea is that in order to authenticate a ciphertext that you receive, you use the classical key, you undo the permutation, then you check the padding. If the padding is 0, okay, otherwise you discard. The problem is that showing that this intuition works, proving it mathematically, it's very, very difficult. And in fact, this problem has been solved only recently in 2018. So you see that so far, quantum cryptography works a little bit like classical cryptography, but with some differences. The differences are not finished here. Let's look at signatures, so RSA, ECDSA, and so on. Classically, what you want to do is you have a message, you have a signing key, you want to generate a signature using the signing key, and then you have the pair of message and signature, and a verifier using a public key can check the authenticity of the message. Can we do something like this for quantum states? That's very tricky. In fact, if you have a quantum message and you want to have a classical signature, this is absolutely impossible. And the reason is basically no cloning, because to generate a classical signature, you would have to consume the message. So you might wonder, is it possible to do a quantum signature instead? It turns out to be impossible as well. The reason is a little bit more complicated, but it's mathematically possible to prove that this doesn't work. What you can do is a quantum signature on a classical message. And finally, you can take a quantum state and do signature and decryption at the same time. This is possible. It's called quantum sign encryption, but it's still impossible to achieve quantum no repudiation, which is instead a property that you can achieve classically. So already in the case of signatures, quantum cryptography starts behaving differently. There are also things that are possible with quantum cryptography, but not with classical cryptography, that are super cool applications. For example, unclonable decryption keys. In this kind of scheme, you have a classical public key, but a quantum private key. If you want to encrypt a classical message, you can use the public key. But if you want to decrypt the message, you need to use the quantum private key. The good thing is that the quantum private key is not destroyed during the decryption process, which means that a user can encrypt messages using only classical information. To decrypt them, you need a quantum computer, but the cool property of the scheme is that your private key cannot be copied, and this is impossible to achieve classically. Finally, the last example that we see is quantum money, where there is a quantum mint, a quantum bank, that generates quantum tokens and classical verification keys. The verification key can be used to verify the authenticity of the quantum token without destroying the token, which gives you a cool way of exchanging values, because the bank mints quantum money, and the money can be distributed to users. The user can validate the authenticity of the banknote by using the public key of the mint. This coin, the quantum coin, can be transmitted to other users. Each user can verify the authenticity of the coin with the public key, but it's impossible to do double spending because it's impossible to do a copy of the quantum token. In other words, who needs blockchain in a quantum world? There is a lot of other applications that I don't have time to go through, but some of these are very cool, and I really want to encourage you to have a look at this. What I want to stress, and with this I conclude my talk, is the message I want to give you is that we are heading to a future where classical and quantum data have to coexist. In this world, quantum-resistant cryptography is not going to be enough. You need also something else on top of it. Don't use the term post-quantum because it's terribly misleading. Start transitioning now to quantum-resistant cryptography and keep an eye on the many exotic applications that are enabled by fully quantum protocols. Thank you for your attention.